Hi, I'm Nikki. Welcome to my channel about game development. This is a video in a series dedicated to learning Unity's animation system. In the previous video, we learned all about creating dynamic animations using blend trees and a single float parameter. Today, we're going to expand upon that knowledge by adding an additional float parameter and learn about two-dimensional blend trees. Alright, let's get going. To get everyone up to speed, in the previous video, we created a one-dimensional blend tree that was dependent on a single float parameter titled velocity. After adding a script to control the current value of velocity through a player's input, our idle animation would transition to the blend tree, where dynamically created animations would blend our walk animation and our run animation. Really cool and helpful stuff. I recommend you check it out if you haven't, because there's knowledge from that video that will be applied today. But now, let's take those concepts to the next level. We'll start today off by returning to Mixamo.com and selecting our previously downloaded character. We will download animations for strafe walking left and strafe walking right, and we'll also download animations for strafe running left and strafe running right. If you're new to the series, go ahead and download idle, walk, and run animations. As we know from the original exporting from Mixamo video, we can leave the keyframe reduction off, 30 FPS for frames per second, switch the format to FBX for Unity, and we'll set without skin because we already have the Mixamo model in our scene. Lastly, we'll be sure that the in place checkbox is checked. We will import these animations to our Unity project folder and return back to our Animator component where we currently have our idle animation as the default state, and a one-dimensional blend tree used to blend our walk and run animations. Let's start by creating a completely new blend tree, rename it to 2D blend tree, and set it as the default state. We can move the old idle state and the original blend tree off to the side. In the parameters tab, we'll notice our leftover parameters from the previous video, two Boolean parameters titled isWalking and isRunning, and a single float parameter titled velocity. Let's add another float parameter titled VelocityX and rename velocity to VelocityZ. Then we'll double click on the blend tree node to navigate us into the blend tree layer. In the inspector window, we'll notice that 1D, for one dimensional, is selected as the blend type. This is the blend tree type that we used last time. When we press down on the dropdown, we have four new options: 2D Simple Directional, 2D Freeform Directional, 2D Freeform Cartesian, and Direct. These are all considered 2D or two-dimensional blend trees. The stated difference is, quote, how the influence of each motion is calculated, and they are all quite different because of this calculation. Our main takeaway from this definition should be that despite each option sharing two-dimensional in their names, these blend trees each have their own specific use cases. We will start with 2D Simple Directional. On selection, we'll immediately notice that the inspector's format has changed. The field titled Parameter will now be titled Parameters, with two drop-down menus currently set to our VelocityX and VelocityZ parameters. If your variables don't match up to mine, simply select them so that they do. Next, for our example, we'll add 7 motion fields. After the second motion is added, we will notice the newly displayed graph. This graph can be interpreted as a standard X and Y axis graph, where our first parameter, VelocityX, is represented by the x-axis and VelocityZ is represented by the y-axis. And the red dot in the center is the coordinate point defined by the current value of VelocityX and VelocityZ. Once we have finished adding all 7 motions, let's set each of our 7 animations: idle, walk, run, and all 4 strafe animations. As we add each animation, we'll see new nodes being added on the graph. We'll discuss these further shortly, but for now, you may notice your position X and position Y of each motion might be different than what's on my screen. Let's go ahead and reset all of them to the origin, 0 for position X and 0 for position Y. Now we'll go through them in order and properly place them. For our idle animation, we'll have it set to 0 on the x-axis and 0 on the y-axis. This is because when the player is not moving, they should not have velocity in the x or the z direction. Taking a look at our character in the scene view, we can see that it is face in the z direction. For this reason, our velocity z is what we will use to drive the character's forward animations. Remember, our blend tree uses the parameter on the right for position y, so let's set our walk animation with a position y of 0.5 and our run animation with a position y of 2. So for idle animation, sitting on the origin of the graph is to be our character's neutral position. Again, where velocity x and z are both set to 0, then we can set our strafe walk right animation to position x of 0.5 and strafe run right animation to position x of 2. And our character's strafe walk left animation to position x of minus 0.5 and strafe run left animation to position x of minus 2. So now that the nodes are set to the correct positions, let's learn what they do. Looking at the graph, we'll notice the color gradient ranging from blue to white. Without selecting a motion, the areas that are more prominently blue are highly influenced by motions, while areas in white are less influenced by motions. If we click on a motions node, the graph will change to display only the area that this particular motion has influence over. And if we drag our red dot around, we'll notice small blue circles starting to expand from the motions that are close to the current location of the dot. These circles are a way of showing us that these particular animation motions currently have influence and weight over the blend tree's animation. Let's try testing out our current blend tree in play mode, but before we do, be sure to disable the script if you have it enabled from last episode. When testing, we'll notice some unexpected results. For starters, if we increase velocity z past a value of 1, our running animation is never blended with our walk animation. And when we test velocity x, our idle animation will blend with our left walk animation, but not our left run animation, or right run animation. What's happening here? I think this might be easier to understand if we fix the problem first. Scrolling back up to our blend type, we'll switch from 2D Simple Directional to 2D Freeform Directional. Voila! Everything now works as expected. So what's the difference here? The difference is actually in the name, 2D Simple Directional. Simple Directional blend trees are intended to only use a single motion for any direction. This is proven and showcased as we increase velocity z. Our blend trees blend between our idle and walk animation, but it does not blend a second time between our walk and run animations. Additionally, it will not use the left strafe run animation because it's in the same direction as the left animation. We'll see a warning stating Simple Directional Blend should have motions with directions less than 180 degrees apart. This is the reasoning behind our left walk animation playing, but not right walk animation. It will not use either of the right animations because both animations are exactly 180 degrees from the left animation. This can actually be proven by making the right strafe walk less than 180 degrees from the left. And this warning is removed if we add an additional animation below the origin. This is because of how a simple directional blend tree's influence is calculated. But we should still note that the additional motions in each direction are excluded from the blend. I found the reason that the idle animation was still playing is because Simple Directional will also accept an animation at the origin. So Simple Directional are not meant to be used for our current setup. They're actually meant to be used for, well, simpler concepts that use less motions. Now that we understand Simple Directional, we also know that Freeform Directional is intended for many animations that can be in the same direction and without a degree limitation. So for today's project, the Freeform Directional blend type is what we'll be sticking with. Now before we get into our code, let's take a look at 2D Freeform Cartesian. If we switch to this blend type, we'll notice that all of our animations still work as intended, and the difference is actually really hard to notice. However, if we take a side-by-side look at the blend graph between Freeform and Cartesian, we'll see that they are in fact different. This brings us back to what we learned earlier. The difference between all three of these blend types is how the influence of each motion is calculated. So what we're seeing on the graph is Unity's difference in calculation for each blend type. I actually found the master's thesis of the Unity employee which these two blend types are based off of. It's rather complex and truthfully well above my current knowledge and understanding. But the main takeaway should be what's stated in the Unity docs. Freeform Cartesian is best used for animations that do not represent different directions, and this blend type can have different concepts for the x and the y parameters, such as degrees. An example would be using vertical and horizontal angles to blend aiming animations. And the last type of 2D blend tree is direct. Direct allows you to control the weight of each node directly and is typically used for facial expressions. Unity has a great video covering this, and I may cover it myself in the future. Awesome. Now that we have a base understanding of all 2D blend types, we know that for our current setup, we're going to use Freeform Directional because we are focused on velocity for both parameters, and we have multiple animations in each direction. Now let's put control of these animations into the hands of the players using our code. To avoid deleting code we wrote for our one-dimensional blend tree, we'll create a completely new script. We'll be applying similar logic that we have in the past, so you may be able to complete this script without even needing to follow along. As a fun experiment, you can try pausing the video and testing your current knowledge to see if you can get the two-dimensional blend tree up and running. Selecting the Ybot, we'll click Add Component, type Script, and select New Script. Let's title our script Two-Dimensional Animation State Controller. Double-click on the newly added script and our IDE will open. So we know that we need access to our Animator component because it's where animations and parameters are stored. In the scope of our script, we'll declare a variable Animator of type Animator, and in the start function, we'll set the reference to the Animator component by using Unity's getComponent function, passing in Animator as the argument. This will search the game object that the script is attached to and find the Animator component. Next, we'll declare two variables that will represent our velocity on the X and Z axis. Below our animation declaration, we'll write float velocity z is equal to 0 and float velocity x is equal to 0. Navigating to the update function, we'll start to handle player input. We'll create 4 Boolean parameters to track when a player presses 4 different keys. We'll write the Boolean forward press is equal to input.getKey, passing w in as the parameter. And we'll replicate this code for left pressed, right pressed, and run pressed, passing in A and D and left shift to each getKey function respectively as the parameters. Each of these booleans will be true or false depending on if the player is pressing down on the pass-in key. We'll now want to create some conditional statements so that we can modify velocity z and velocity x if the keys are pressed. Let's start with one we are familiar with from previous episodes. We'll write if forward pressed velocity z plus equals time.delta time times acceleration. As a reminder, time.delta time is the amount of time since the update function was last called, and we will need to declare our acceleration variable below our velocity variables. We'll write the public float acceleration is equal to 2. By adding public to this declaration, we'll have access to this in the Unity editor. And before continuing with our conditionals, we'll also create a deceleration variable for when the player is not pressing the keys down. Let's duplicate and rename the acceleration code to deceleration. Alright, let's now create 2 more conditionals to handle our changes in velocity on the x-axis, which will control our strafing. We'll write if left press velocity x minus equals time.delta time times acceleration. And then we'll write if right press velocity x plus equals time.delta time times acceleration. We use minus equals for left because in our blend tree, we set the 2 left animations to the values of minus 0.5 and minus 2. If we enter play mode now and attempt to use our newly set up controls, nothing will happen. This is because our velocity x and velocity z variables are local variables to our script. But remember, we create a reference variable to our animator when we first created our script. So we can actually access our velocity x and velocity z parameters with the help of this reference. At the bottom of our update function, we'll add the code animator.setFloat and pass in 2 parameters. The first will be the string VelocityZ, and the second will be our own VelocityZ variable. Next, we'll duplicate this code and just change VelocityZ to VelocityX. Let's test our new controls in play mode. Success! Holding the W key has our velocity Z increasing, and holding A and D will decrease and increase our velocity X accordingly. Awesome, but there's definitely some improvements to be made. To start, we need to implement deceleration for both axes. We should also cap the maximum and minimum velocities when each button is held down. We also want to incorporate our left shift to run feature. Lastly, we can refactor our code for better performance. Returning to our code, we'll start by adding the maximum and minimum values to each of our current conditional statements. For forward press, we'll add a maximum value of 0.5 because we set our walk animation at 0.5 of position Y on our graph. We'll then set a minimum value of minus 0.5 for left press and a max of plus 0.5 for right press. The thing is, we only want these minimum and maximum values for when run press is not true. So we'll add that condition as well by adding exclamation run pressed. Let's implement deceleration for our forward movement. We'll write if forward is not press and velocity z is greater than 0, then velocity z minus equals time.delta time times deceleration. We can also add the conditional. If forward is not pressed and velocity z is less than 0, then set velocity z equal to 0. This will reset our velocity z in case the deceleration ever overshoots our minimum value of 0. Next, we'll implement the deceleration on the left and the right. We'll write if left is not pressed and velocity x is less than 0, then velocity x plus equals time.delta time times deceleration. We'll duplicate and modify this code for the right, stating if right is not pressed and velocity x is greater than 0, then velocity x minus equals time.delta time times deceleration. This code will slow down our character when the respective directional keys are not pressed and velocity x is not equal to 0. Now let's implement a similar reset that we have for forward press, but for when both right and left are not pressed. Stating if left is not pressed and right is not pressed and velocity x is not equal to 0 and is either greater than minus 0.05 or less than 0.05, then set velocity x equal to 0. For this logic to work properly, it's worth noting that we may need to adjust the 0.05 values, depending on what the acceleration and deceleration values are. Testing this in play mode, we'll now see our character decelerating in all directions and locking at 0 for both velocities when all keys are not pressed. Perfect! So we've implemented our velocity min and maximums, and we added deceleration. Let's proceed to handle running. If we take a look at a lot of our conditions, we'll notice repeating float values. In the process of adding our running functionality, we're going to refactor these float values by replacing them with a single float variable. And the best part is, we can reuse this value to work with both walking and running. Below where we declared our deceleration variable, we will declare two new public float variables called maximum walk velocity and maximum run velocity. We'll set our maximum walk velocity to 0.5 because we place our walk animations all at 0.5. And we'll set maximum run velocity to 2.0 because in our blend tree graph, we set the running motions to 2.0. In our update function, we can make a new float variable called currentMaxVelocity, which is equal to either maximum walk velocity or maximum run velocity depending on if run press is true. This code is called a ternary operator, and will set the variable equal to the first option after the question mark if the statement before the question mark is true. Otherwise, it will set the variable equal to the second option. So in our case, if run press is true, then it will set the value equal to maximum run velocity. Otherwise, it'll set it to maximum walk velocity. We can then replace the conditions where we are using 0.5 with the currentMaxVelocity. Doing so will allow the player to exceed the 0.5 limitation when they are holding left shift, because it updates the currentMaxVelocity in the conditional statement, and our acceleration will continue to increase. Then we'll remove the condition for when run is not being pressed. Testing this in play mode, it works. But now let's set some caps for the increase in velocity. We'll state if forward pressed and run pressed and velocity z is greater than current max velocity, then velocity z is equal to current max velocity. We would ideally do something similar for walking. However, replicating this logic without run press and with current max velocity would set the velocity to 0.5 immediately after letting go of run. We'd prefer to decelerate to the maximum walk velocity. So we'll write else if forward press and velocity z is greater than maximum walk velocity, then velocity z minus equals time.delta time times deceleration. But this leads to unwanted and jittery results. We'll write one last else if statement stating else if forward press and velocity z is less than current max velocity and velocity z is greater than current max velocity minus 0.05, then set velocity z to the current max velocity. And we'll copy the velocity logic to the previous else if statement, but we need to reverse it because we're coming from a deceleration standpoint. What this does is check to see if we're close enough to the current max velocity, and if it is, then we should just set it to the current max velocity. In play mode, we'll find that when we press W, our forward velocity increases and maxes out at exactly 0.5. Holding run will increase our velocity toward the 2.0 limit, and again, it will reach exactly 2. And if we let go, our character decelerates back down and locks in at 0.5 once again. Perfect. We can replicate this logic for left and right pressed. We'll copy and paste this code twice, and we'll replace forward press with right press and left press in each block of code. For left press, however, it can get quite confusing. We need to also modify the current max velocity so that the value is negative. And we will need to switch a couple of the less than greater than signs. We can test this again in play mode to make sure that everything works exactly as we intended, locking at 0.5 and 2 and decelerating. Our last task for today is going to be a little code refactoring. Refactoring is important for both performance and readability of our own code. We'll definitely appreciate the small amount of time we take now to refactor in the future when we come back and try to understand our own work. We'll start with the refactor we have done in the past. We'll declare two int variables, VelocityZ hash and VelocityX hash. In our start method, we'll set each to animator.string2hash, and we'll pass in the string version of the parameter we are using in the setFloat function at the bottom of our update method. Then we'll replace the string version with the newly defined and set variable. Next, we'll replace each string argument in our input.getKey function with their associated keycodes. Just another small performance-saving refactor. And our last refactor is just for readability. If we take a look at our update function, it's massive. And without the comments above each, the code is simply daunting to understand. Let's extract our blocks of code into two new functions to clean this up. The first we create will be called changeVelocity, and we'll pass in each of our local variables we have set at the top of the update function. Then we'll cut and paste our blocks of code associated with increasing and decreasing our two velocities from the update function and paste them into the new function. And we'll do the same for a second function called lock or reset velocity, passing in the same parameters and moving the remaining conditional statements from the update function to this new one. Now we just need to call changeVelocity and lock or reset velocity in the update function and pass in all of our variables as arguments. One last time, we'll test this in play mode and we'll see that everything is still working as intended. Amazing job today! In the next video, we're going to take a look at how to retarget our animations from our Mixamo character to our own. We'll continue the series based on Unity's animation system by learning to make more complex animation state trees. We'll also take a look at animation state layers and animation-based events. I want to take a second to thank everybody for your support. This channel has grown a lot faster than I ever expected it to, and a lot of that has to do with all of you. The positive reception is really what gets me through some of these early morning wake-ups and the late nights I spend dedicated to each video, so thank you so much for your support. I really do appreciate it. If you're interested in joining me and a growing community, there's now a channel Discord. The link is in the description. We've already had some great conversations and we're really helping each other out when it comes to coding and learning how to use all these animations. And as always, if you learned something new today or found the video entertaining, please consider pressing the like button and subscribing to the channel. It helps me out and lets me know that we're headed in the right direction. That's all for today. Thank you for watching, and I'll see you in the next video.